This section is about conservation of angular momentum and moment of inertia. So, you've jumped on a spinning thing, a swivel chair, in order to slow it down. And it works. Your added mass slows the rate at which the chair spins, but it's still spinning too fast. What can you do to slow it down? You stick out your arms and legs and it works, the chair spins more slowly. But why? You've not added any more mass, so it can't be that. What you have done, though, is increase your moment of inertia. That is, you've changed the way that your mass is distributed about your axis of rotation. The further away your mass is from the axis about which you are rotating, the harder it is for something to spin you round in a circle. So for the same input energy, you spin more slowly. This is known as the principle of conservation of angular momentum, and it's useful to think of it as the rotational equivalent of conservation of momentum, which applies to motion in a straight line. Remember that the principle of conservation of momentum states that the momentum of a system stays the same if there's no external force. Momentum before equals momentum after. Well, the principle of conservation of angular momentum states that the angular momentum of a system is conserved if there's no external torque. Torque is also known as moment, and it's the rotational equivalent of force. Let's also compare momentum and angular momentum. We've seen that momentum is given by mass times velocity. Well, angular momentum is given by moment of inertia times angular velocity. The angular velocity is the rate of change of angle, how fast the object is spinning, measured in radians per second. And the moment of inertia depends on the mass of the object and how far that mass is from the axis of rotation. For example, for a point mass m at a distance r from the axis of rotation, the moment of inertia I is given by I equals m times r squared. Let's think about what happens if we move this mass to double the distance from the axis of rotation. The moment of inertia becomes 4 times bigger, so the angular velocity must become 4 times smaller to conserve angular momentum. Examples of this phenomenon are ice skaters drawing in their arms to spin faster, or cyclists spinning faster as they bring themselves and their bike closer to the axis about which they are rotating. You can also easily see this yourself by spinning on an office chair and drawing in your legs, or by spinning a mass on a string and noting that it is harder to spin the mass at the same rate when the string is longer. We've said the moment of inertia for a point mass is mr squared. What about for a more complicated rigid body? We will see that we can calculate its moment of inertia by splitting the body up into lots of little point masses and adding their individual moments all up, a bit like calculating the centre of mass. For example, when we do this for a circular disk of mass m and radius r, we find that the moment of inertia about an axis through its centre is half mr squared. It's important to emphasise that the orientation of the disk affects the moment of inertia, not just its mass and radius. For example, if we rotated it instead about its diameter, the moment of inertia is 1/4 mr squared. This is less than the first orientation we considered because more of the mass is now nearer to the axis of rotation, so it becomes easier to rotate. A final thing to note is that objects have a preferred axis of rotation about which their rotation is stable. For example, a rectangle will rotate stably about an axis through its centre where its moment of inertia is maximum, or about an axis through its centre long ways where its moment of inertia is minimum, but not about its short axis where the moment of inertia is intermediate. Here the motion becomes unstable. Mass. How hard it is to accelerate something. Moment of inertia. How hard it is to accelerate something round in a circle.